Okay, now I'm recording. All right, so today we're going to be talking about chapter 2 and talking about combinational systems, switching algebra. So we're going to be talking about Boolean algebra, which you may already be familiar with somewhat, and then how that's connected to logic gates. And these are these chips that can make decisions for you. So in that last class that you've had in electrical engineering, we talked mostly about resistors, capacitors, inductors, and power and voltage. Here we're talking about a lot of ones and zeros. So not so much of this right over here. It'll be more of this kind of thing here, where we basically have ones and zeros is what we're going to be referring to most of the time. And as we talked about 1 week ago, um, logic 0 corresponds to 0 volts or ground, and logic 1 corresponds to 5 volts for most circuits. Sometimes in the Arduino world especially, they use 3.3 volts for that. But for the most part, we're just focusing on having 2 voltage levels to speak in a language that a computer can understand. We're talking about this chip right here in particular. Well, it doesn't really have a number on top of it. I suppose I can put a number on top of it. A very common one that we start off with is the 7400. When you get into lab, you'll actually get these and you'll get them out of the shells. And if you look really closely at the top of these, you can actually see the lettering. I think I got an image here of one that was blank on purpose. But you'll see one that's a 7400. I happen to know that that one's a NAND gate. And you want to be careful about these pins because they'll bend as you push them into the breadboard across the valley of that. But Dr. Ochoa and your lab instructor will be careful with you on that, in distributing those to you. I'm excited that you'll be able to get your hands on these things this semester. I'm looking forward to visiting the lab when y'all are there as well. Make sure you mask up, and we're going to stay. I think everybody's going to work independently in this lab. So no lab partners really, just everybody's going to stay 6 feet apart or further during the lab as we do this. And usually this notch, see, here's what I can do, which is difficult to do in a lab. I can show you that that notch right there exists. Instead of having to get close to you, I can just kind of zoom in on it right there. That basically means I need to put that to the left on my breadboard. I think I have another picture on the next slide here. Yeah, see this little notch right here? I need to get some different color though. Let's go back to like navy blue is our color for the semester. You see the notch right here. It basically is telling you, put that across the valley of your breadboard. So there's these holes back like this. And those 5 holes, as you may remember from electronics lab, are connected in a sense that behind the plastic, these 5 right here are connected to one another. Now, this really goes into the first slot right there, but you get the idea. All right, let me just undo a lot of that stuff. Okay, so the notch that's on the left-hand side tells you where pin 1 is, and you go counterclockwise from there. So there's pin 1, and then you go all the way around from there to this. Now, just like your brain cannot work without some power, in the same way, this circuit right here, this chip, this integrated circuit cannot make a decision unless you power it up. And so for that reason, what you do is you normally tie this right here to positive 5 volts, and you'll do that on the breadboard. And then you tie this one over here to ground. So there's a ground symbol on there, and you'll just connect it there. And then what you do is you say that you look at this symbol, and I'm going to familiarize you all today with these symbols. And you'll realize today, or after our discussion today, that this right here, 1 and 2 are inputs, and number 3 is an output. You'll kind of get a feeling for it. You can kind of see the way the circuit symbol is pointing that's kind of the trend. That's the output here. You'll also notice in D2L that I have basically a whole module dedicated to data sheets. And so when you're an electrical engineer or a mechanical engineer and you want to make a device that makes a decision with a decision-making circuit, you often have to look up the data sheet to see that, oh, okay, pin 9 and 10 are inputs and pin 8 are outputs. That's kind of what you get from the data sheet. You get a lot of other stuff like what temperature it can operate at and still be reliable. They come in these different, they come in different packages over here as well. This is called a PDIP package. Not like you need to know that, but sometimes they make the separation between these pins different for different purposes. If you want to make it really a small circuit, you can get these things to be almost microscopic when you're working on them. All right, so let's get into these gates here. And so what you want to do in your notes is basically say that the first gate that we're going to talk about is a blank logic gate right there. So there's going to be a word there at the end, and I'm not going to do the and because I noticed that I forgot to erase it a minute ago. And what we're going to do is talk about 6 logic gates that you'll encounter in lecture and in lab. And we're going to discuss what function they serve. And then as we describe them, what we're going to do is connect them together to make more complicated decisions. So these 6 logic gates make very fundamental decisions. And let me see if I can start it off here. The 5 things we're going to be talking about for each one of these logic gates, which is an integrated circuit, is we're going to talk about the circuit symbol, what the truth table for that component looks like, how we write it in terms of an equation, what does it mean to say daisy chain, and then also, is it possible to have more than just 2 inputs? See over here, we just had 2 inputs for those right there and 1 output. But in some of these gates, it's possible to have more than that. All right, so the first thing I'm going to do here is circuit symbol. The first circuit symbol I'm going to show you has a curved back to it and then a pointed front, almost like the Star Trek communicator badge sideways, almost like that. And then this is going to be the output, and this is going to be the input over here. So when you all build these circuits and do your homework and do quizzes, be very careful about case. By case, I mean we're going to use lowercase here like that, but some cases on your homework, they'll ask you a problem, they'll ask you a question, and they require that you use uppercase. So just make sure that during the semester that case matters here. Just like in programming, oftentimes case matters. We're going to do the same thing here. That's it. That's the circuit symbol. Now we're going to look at the truth table. That's the next thing. So I'm going to check off the list as we go down here so you can see where I'm at. And at the end of this, I'm going to ask y'all in the chat what kind of gate this is. So circuit symbol there. All right, next. A and B are our inputs, and normally we have that on the left-hand side of our truth table. That's what this is here. And the possible values of the input, we're going to restrict. Instead of having any old voltage coming in there, we're going to say you can only have 0 volts or 5 volts relative to ground. So what's kind of hidden in this diagram over here is that there's this line down here, and I'm gonna draw it and then quickly erase it. But basically, you could put like a multimeter right here and measure the voltage out between those 2 points right there. In a similar way, you could have a switch that's basically saying that the wire B is either at 5 volts relative to ground. Let's see, don't I have a laser somewhere? Okay, there we go. 5 volts relative to ground, or it's 0 volts relative to ground. And the same thing is true for A. But we're not really looking at all the details like that. We're just trying to figure out what, in a black box kind of way, what does it do? And so the answer is, if you do this, it's 0, 1, 1, 1. So the output will be high for all of those things right there. All right, so just making sure everybody's here with me. What kind of logic gate is this? What word do I put right here? All right, and so just answer that in the chat privately, or actually, let's do it privately. All right. And what kind of logic gate is that? You know what? I really haven't described what it does. Let me see. I see some answers coming in there. Let me see if I can lead you in the right direction. The output is high if A if A is high or if B is high, or both. So it turns out it could be an if then else. Yeah. Okay. Okay. Good. Good. All right. So I think I'm asking the question too soon. Okay. Okay. I feel like I'm teaching now. This is awesome. All right. So the answer to this is or. This is an or gate only. So all it does is perform the or operation. I think I asked that poll question way too soon, which I'm thankful for y'all's feedback there. But this is called an OR gate, like this this symbol right here is referred to as an OR gate, and you can get 4 of them on one of those chips. Okay, gotcha. Now let's go to our checklist. Suddenly I switched over to red for some reason. Let's talk about Boolean expression. So by that, I mean, I want to write an equation. I want to write an equation for C. And so we need to decide how we're going to do algebra in a world in which we only have 2 numbers, 0 and 1. That's it. Imagine a keyboard that has 2 gigantic buttons on there, a 0 and 1, and try to imagine texting somebody that way, right? You'd have to encode the 1s and 0s and send an A and then send a B and so forth like that. So that's what we're doing here is we're trying to develop a mathematics that doesn't have 0 through 9, but only has 0s and 1s. And that's referred to as Boolean algebra when you do that. That's the word. It's a 2-state logic algebra. And the symbol that we're going to use for OR is this. And you might say, oh, that's a plus. And my answer, my response to that is, no, it's not. It's an OR symbol. So in this course, this does not mean plus. It means OR. And if you get into modern mathematics, I think it's Math 311, or it used to be 311. They do that kind of thing where plus doesn't really mean plus and multiply doesn't really mean multiply when you have a new kind of number system. All right, it's not really going to be that complicated. So anyway, here's our Boolean expression here. The plus means OR. All right, so what does it mean to say daisy chain? Daisy chain means that, let me write a simple, make a simple sketch over here to the side. Daisy chain. Let me check with audio. Anybody want to unmute their mic and try to explain what daisy chain means? Excuse me, I almost lost my voice there. Does anybody want to unmute your mic, Chase?
I was gonna say, when I hear daisy chain, I know that you can like link a bunch of things together to make a daisy chain.
That's it. Yeah, and so what you can do is think of like a daisy flowers chained together like that. And he's talking about, linking things together. That's a perfect way of seeing it. So there's a couple of ways we can do it. One way is to have the output of this gate be fed into another OR gate like that. In this case, we have an A, B, and C input, and the output is D, and the output would be A or B or C. So you can begin to see that you could build a circuit with these wires. Each one of these things that I'm drawing, by the way, those things right there, those are all wires that are going to get a chance to connect in lab and make a miniature little brain. And you're going to be building bigger brains throughout the semester as you become more comfortable with this. Now, there is a common mistake that some people make, and I'm gonna go and make that mistake, and then you don't have to go any further than I did as far as note taking. But I'm going to go back and make a mistake on purpose and then fix it. You could have 4 inputs, and that's not the mistake, because you could have C and D like that. The mistake that people make is they just tied those wires together. But from an electrical engineering point, you can't really do that, because if this wire right here is 5 volts and this wire over here is 0 volts, in other words, ground, you basically have a short circuit right here and you're going to burn up the wire. So you really can't tie the outputs of wires together. Can anybody guess, and you can use your microphone again, what the correct way to do this is? Does anybody have a guess as far as how do you correctly do this? Not tying those wires together, but what should we do instead? Anybody?
Put another OR logic gate.
That's it. Put another OR in there. So you do have to use more of the chip to do that. And the output here would be F. And then the equation for this, the Boolean expression it's called, is going to be A or B or C or D. The final thing I want to talk about before we move on to the next gate is what if can you buy a multiple input OR gate? And of course the answer is yes. Multiple inputs. So now we're talking about this right here. So there's daisy chain and there's that. This seems kind of wasteful over here, right? You're using a third, well, I guess 3/4 of a logic gate of a chip if you are seeing that they come in packages of 4 here. They call this a quad NAND because you can put 4 of these NAND gates on there. All right, so let's go over here and I can show you that the way that works is you just make a bigger symbol like this. It doesn't have to be a bigger symbol, I don't suppose. That could be F and then like this right here. So you can purchase a different chip from Mauser. That's usually who we buy things from, that has, basically an OR gate in here, and it uses 4 of these as inputs and 1 of those as outputs. So the internal wiring of it looks a bit different, and data sheets will bear that out and allow you to use a 4 input OR gate. But if you don't have that, if you don't have this, then you just go back to your daisy chain approach. It kind of depends on what you have, right? So if you're stranded on a desert island only with OR gates, you got to do it this way right here. All right, any questions about that kind of gate? All right, we're going to go faster through these other ones now that you see my 4-step process, right? Actually, it's 5 steps, right? So we're going to go through the 5 steps: circuit symbol, truth table, Boolean expression, in other words, equation, daisy chain, and multiple inputs if that's even possible. All right, so the next one I'm going to do, and I never really know what order I'm going to do them in until I get into class. The next one I'm going to do is I'm not even going to write the words here. I'm just going to do them. Okay. So in the interest of time, I'm going to do this one, curved back, pointed front, just like before. But I'm going to put a bubble out there. Output C, input A, input B. Then I go immediately over to truth table. A and B, output C, the possible values of inputs, 0, 0, 0, 1, 1, 0, 1, 1. And what this means right here, right there, it means not. So the bubble at the end of logic gates means not. So this right here, that means not and, as we'll find out in a moment. All right, so basically what we do is go back to the right color pencil, I guess. And we look at this truth table and we say, this right here was an OR right here. That's what this was. It was only on if A or B or both of them were on. Now we need to do, on the next one, the opposite of that, which is 1, 0, 0, 0. All right, let's see if y'all are with me. What word goes right here? And let's send me a private message on that one right there, and I'll wait until I get about 5 answers. What word goes here? I think I actually accidentally said it. Yeah, that's right, Carly. That's right, Miguel. Chase, Jacob. Okay, good. Now this is, it's the opposite of or. So we call it not or we call it nor. So that's the name of this gate. And you'll notice it's actually on the inside cover of your textbook. One of the cheat sheets that you're going to use for homework number 2 is basically the inside cover of your textbook that has each one of these logic gates and their truth tables on there. The logic expression, okay, so we did that. The logic expression looks like this. C is equal to A or B not. So let me go back to my green. This prime out there in the world of this author, it means not. In some textbooks, what they do is they say put a bar over it like that. But this will be the only time you see that, because in this book they use prime for that. And I think even in multisim, which we'll be using for lab and lecture, they're using a prime for that as well. You know what? I think you'll got a handle on the daisy chain in multiple inputs. So I'm not going to redo that for this one. On this one, I might do it on the next one. But those are the three things I want to talk about: circuit symbol, truth table, logic expression for this NOR gate. Let's do another one. Okay, flat back instead of a curved back, a D front, so it's not pointed out like this right here. This is my circuit symbol, inputs A and B, output C. Truth table, possible values of input. Oh, I counted wrong right there. Check that out. See that I need to count basically from 0 to 3. So there's 0, there's 1, there's 2, there's 3. So let's not forget, number conversions from last chapter there. Output is C. This one is that right there. Let's see if y'all are ready in the chat. What word do I put right up here? What kind of gate is this? What kind of logic gate? What kind of integrated circuit is it? And now you're with me. Okay, so see, I feel like I'm making progress today. Y'all quickly caught on to that after I got past the first couple of gates. The way that we write the logic expression for this is you say A and B. I don't think they ever use like an X for times. It's always like a dot. In fact, after a while, we'll even get rid of that and we'll just say A and B. Now, it's okay that if in the beginning of our conversations that we have in lecture and lab that you accidentally say times, like A times B, or over here, it's okay if you say, for that right there, it's okay if you say A plus B for at least for a week or so. But after that, it's like being in an astronomy class. You can't call it astrology anymore after a certain time. So we have a new math that we're kind of doing here. We're using a new math in electrical engineering, or engineering in general here. And so we have to think of this word right there, that dot, we have to think and, okay? And it's not the same thing as multiply. We have to think and. When we see this symbol right here, we have to think and. I'll do a couple of a quick daisy chain just for this one, just to show you with a quick visual what it would look like. And see, there's a problem that I'm kind of messy on that, right? Well, I think multisim is going to help us keep, a better looking diagrams for this, because it's easy to kind of do this quickly and not cleanly. Multisim will keep all the straight lines for us there. And you can have a multiple input AND gate. I think I've seen as many as 8 inputs for that. So you can either find this one on the shelf or this one right here. I think this is a 7408 chip, and then I think this is a 7411 chip. But don't quote me on that. Okay, you'll just basically get them out of the shelf, and then you'll kind of look up the data sheet and realize what they do at that point. Any questions so far? Good. All right, so let's go a little faster, and I got 2 more surprises for you, 2 more surprise gates. And I got one that's easy because we're about to do really fast. So this one right here, we've already talked about this one. Output C. You know what? I'm going to change this up a little bit just to let you know that you can change the case and the letters. So it could be X and Y, and then output Z, capital letters. We're going to get used to that as we encounter the homework. In which case you want to put a capital X, a capital Y, capital Z for the output, vertical line separating the two, count to 3. And then you say, well, what kind of gate is this? Well, over here, we have to think that the output is high if A and B are on, right? This and this have to be true or 1 before that's 1 over here. So this over here, we're going to do just the opposite of that because of the not bubble right there. Don't forget that that means not. Okay. And so we need to do the opposite of that, 1, 1, 1, 0. You might say, well, isn't that just the opposite of a NOR? Not really. See, a NOR looks like that, 1, 0, 0, 0. A NAND is 1, 1, 1, 0. So it is different. The Boolean expression for this is Z is equal to X and Y. And then you got to do quantity prime. As we'll find out, this is not equal to X prime, Y prime. It's just not. I mean, it's actually it's not illegal. It's just wrong. It's not equal to it at all. We'll see something called De Morgan's theorem that shows that they're not equal. So let's make sure that we always put that not on the outside over here for that right there. Okay, do I need to do daisy chain again? No, not for this one. Multiple inputs, no. I think we got the picture on that. Okay, question for the chat. What kind of logic gate is this? What do we think when we see this symbol, this equation, that truth table? What word should we think of? All right, now we're getting it. How about a couple more people answer? Okay, there they come. All right, good. And normally, I don't really know why we do this. It's always just capital letters all the way through. I never really thought about it, but capital N-A-N-D, NAND. So NOR is actually a word, right? But NAND is not really a word except for in electrical engineering or engineering in general. All right, I got a surprise for you. Another surprise gate. Got 2 more to go that you'll investigate and you'll put on a breadboard. And when you see those lights light up, it's like, wow, this circuit is really making a decision. So we're just doing theory right now and learning about symbols and how we can talk to each other about how you build a circuit. Next one, curved back twice, pointed front like that. I can't remember if the line goes all the way. It kind of depends on which textbook you're using. So double back, curved back, pointed front, output C, inputs A and B. Okay, let's change letters again, just so we can keep it a little different. Let's use like lowercase w, x, y. Now, sure, whatever. It doesn't really matter as long as you're consistent, right? So then you have the w and the x over here, and the output is over here. You count to 3 again, 0, 0, 0, 1, 1, 0, 1, 1. The output of this gate looks like this. That's odd. And then the equation for this, the logic expression, we're not going to do daisy chain or multiple inputs for this one. The way you do this one is you say y is equal to w plus sign with a circle around it. And I did say plus. I wasn't supposed to, but it's a plus sign, right? And you put a circle around it to mean, you know, that double back thing right there. Does anybody want to guess as to what this is with your microphone? I don't know if you've ever encountered anything like this before.
Is it a notch gate?
It's not a NOT gate.
Exclusive OR.
Exclusive OR. Okay. So why do we call it exclusive OR? Because the output is 1 if X is on or if Y is on. I'm sorry, X is on or W is on, but not both. So it's exclusive. All right. So here's a new word for you, XOR. So that's what this means right here. We have to think XOR when we see that kind of pattern. When we see that either one, but not both, being exclusive about it. We have to think of XOR when we see this right here. We have to think of XOR when we see it right there. So double back, plus sign with a circle around it, and also a truth table. And so that is XOR. All right, one more to go. Oh, wait, I ran out of pages. Okay, I think I'm gonna have to just erase this one and do the last one. I think I forgot to re-upload the one with the 6th page on it. I made a mistake there. So what we're gonna do is I'm gonna erase this one. Hope I'm still recording. Yeah, okay, still good on time. And I'm just gonna delete that since I've already caught it on camera. The last circuit symbol we're going to talk about is a triangle with just a bubble. Somebody guessed it already, right? Output could be, I don't know, let's just do output, input A, output C, just because I don't even know why. And so the possible values of A are 0 and 1. The output here is 1 and 0. So in the chat, while I'm writing the equation, privately tell me what kind of gate this is. What word goes right there? Somebody already guessed it a minute ago. What word goes right there? So just guess in the chat. I'm going to write an equation for it right here. So there's my truth table. There's my logic symbol. And I want to do the Boolean expression. C is equal to A prime. Or the way that you would say that would be not right there. Okay. So the way that you would say this phrase right here in this class is you would say C is equal to not A. So you kind of throw the word in front of it instead. C is equal to not A when you do that. I like how you were thinking this. Some of you put an XNOR in there. So if you're interested in an XNOR, I don't think you'll encounter it in the course. By the way, there's no way to daisy chain this together. Well, I guess you could do this, right? But that would be what's the point, right? Because then you would have like an input A and the output would be C, which is A prime prime. And we're going to learn some Boolean theorem that just equals A. So it doesn't do anything. It basically turns it back to what it was before. So that's, I guess, kind of a way of doing daisy chain. But technically, it's not daisy chain because there's no like multiple inputs. So you cannot have a multiple input NOT gate. Since somebody mentioned this in the chat, I will go back and do one more. Okay, I'll add one more to it. And I'll do it really fast. Oh, wait, I don't want to duplicate. I want to delete. Okay, and you don't even need to sketch this one down if you don't want to. I just want you to guess privately in the chat what this is called. One of you already guessed it. This is the opposite of an exclusive OR. And I'm not going to do daisy chain or multiple inputs. Okay, and then what y'all put in the chat, yeah, your favorite superhero, you guessed it, it's XNOR. XNOR. Sometimes this is called the equivalence gate. The reason why it's called that is because the output is high if they're equal to each other. If A is equal to B, then it's that. But most of the time when we see this, we're going to say an XNOR. I don't think we encounter it very much in this course beyond today, but it's good to know that if we have it in lab and if it helps you solve a problem, by all means, go for it. Okay, let me make sure I did everything. I'm supposed to go to, oh yeah, okay, I'm supposed to go to the homework next. So let me shut down Zoom over here and go back to my PC.
Well,
And,
what was your what was the second to last one? My computer Wi-Fi was cutting out real bad.
oh, the second to the last one was a not gate.
Okay.
And then I'm going to post a video for that. So in case you need to get that screenshot of that too. So yeah, I'm going to record and then I'll post it into D2L as well. Yeah. Now these are located on the inside cover of your textbook. Let me see if I can screen share you all that part of it. So I'm going to go over here and go over here. Load up Kindle. All right, so this is the way that I bought my textbook here. Oh yeah, by the way, if you're now getting into homework 2 and your book still has not arrived, then I can, I guess, get you the PDF for chapter 2, but you got to get the book pretty soon. Let's see, why is it doing that? Okay. And so what I did was I went to Amazon and I just purchased the book so that I can load it up in the Kindle desktop application. And this down here is the front sheet. So if you all look inside the cover of your textbook, if you already have it, you'll see this is over here. This is for class on Monday. But what we just did was all of this stuff right here. So if somebody was asking about the last one I did, and it's this one right here, the not gate right there. So I think I've done all of those. Oh yeah, and even did the exclusive NOR down there too. All right, so I think I did all of that inside cover of your textbook. It will be available to you as well on during the exam. So you don't have to memorize this stuff, although it kind of helps to do that. All right, so let's get started on a couple of homework questions. And y'all can feel free to ask a question along the way while I'm getting you to the next homework assignment. So I think what I gotta do is go back over here. Okay, so to get to the next homework assignment, you go to content, and then chapter 2. Oh, it's hidden. I don't know why it's hidden. Let me make that visible to everybody. And then it's just right here, the Google document. And I noticed that some of you like to print it out and write in it. Write in the document and then scan it in later, and that's perfectly fine. I think what I did was I made like here's a YouTube video that shows you how to use the Office Lens mobile app to scan in your paper documents if you'd rather do it that way. Okay, so let's get rid of that and that and that and that and that and that. Okay, so let's go into this from right here. Got 8 minutes to kind of get it started. Pull this over here to the left-hand side. And as always, what we're going to do, I don't see anybody in the document yet. So you could just continue to watch what I'm doing here. Or I haven't shared it yet. Is that what y'all are saying? Wait. Yeah, Monday the 25th is the due date there. Right. All right. Let me know. Can y'all see the screen okay? Half of it's black. Half of it has homework 2 on there. Okay, it's there. Thank you. And now what I want to do is pull up the Kindle over here. See if I can slide that right there. And then go over to chapter 2. And then go down to the exercises. It's got a lot of solved problems in there. I really highly recommend those if you get stuck on a homework question and it's like after hours. All right, now how can I get this out of the way? Oh, yeah, right there. Okay. So the question we're going to be working is E, and then you're going to be doing F as homework. So after the time runs out today, I'm going to continue. I'm just going to stop the class, and then, I'll just be in the class by myself, I guess. And I'll make a video that kind of walks you through every other problem. So just like I did for homework 1, I'm going to do these 2 right here, and then you're going to do those 2. And then I'm going to do A, and you're going to do B. And I'm going to do A, you're going to do C. So I'll do an example for every one of them. I learn by example. I think it's a good way for you all to do as well. Looking at 1E, Let's go down to that problem and just see how far I can get. Oh, great. I happen to pick one that has like a split on 2 different pages. Let's see. Starts on page 100 in your textbook. Okay, and there's half of it down there. It says a system. Let's see if I can just say fit. Okay. A system has one output F, which is why I put a capital F right there. The problem that you're going to work, which is 2F, has an output Y, which is why I put a Y right there. It has 4 inputs, A, B, C, and D, and I got all possible combinations right over there. And each one of these pairs represents a 2-digit binary number, ranging from 0 to 3. The second one, is it capital A? Oh, okay, so it's apparently capital A. So A, B, C, D, so make sure you do that part. I just talked about the importance of, title case or upper and lower case. And so A and B represents one number, and then C and D represents another number. The output F is to be 1 if and only if the sum of the 2 numbers is odd. So in the notes, I'm just going to say that my first number for that 0, 0 right there, I'll color code it like that. Maybe zoom into 150 to give you all a better view. My first number is that. And then I'm going to add on to that my second number right there. Paint it green so everybody's following along with me. Is also 0, and then that's equal to 0. Paint it green. Okay, it says that the output F, that's this column right here, is 1 if and only if the sum of them is odd. A 0 is not odd. I guess it's even, so we're going to put a 0 there for that. Similarly, on this next one, we do 0 plus 1, and we get, 1 for that, and so the answer is odd on that one. Am I doing this in the original document? I guess I am, which is okay. That's all right. So if you're all are about to copy this document, that'll be fine. And I did that completely wrong. Oh wait, no, that is right. That's the number 2, and then that's an even number, like this. All right, and then like this, 0 plus 3 equals 3, and then that's an odd number, so I put a 1 right there. And so you're going to do the same thing for all of those right there. I did want to mention something about your problem that's different than my problem F. And since I only have 3 minutes, I think it's probably a good idea to do that. All right, so you're working F, which is right there. I'm going to zoom in, maybe 150%. All right, so you still have the same situation right here that I do. You have a system of 4 inputs. Okay, great. I just realized something, that they're using different cases. So what I'm going to do here for everybody is just insert a column right here. We're going to insert a row to the left, like that. And we'll just copy this guy right here. Why did I need to do that? Well, because it's lowercase, A, B, C, D. It's lowercase in this particular problem right over here. So A and B represent one number, but you're not going to use the case where it's 3. You just don't care about that. And then C and D represent the other number, and then our output is Y right there. So the reason I put X there is, well, let me see if y'all know this in the chat. Do you remember from last time what X means? And I'm going to highlight this while y'all are answering. I'm going to put this purple to indicate why I am doing that. Let's make that purple. What does X mean? That's a question for the chat. You can answer privately there. And you see this corresponds to 3, so I don't really care about that. Oh, look at that. There's a lot of 3s right here. We don't care about any of those. So what does X mean? We don't even have to do any notes in here. I mean, that's kind of optional. Basically, what they're trying to do is get this column, but the notes can't help. All right, did I miss any of them? Oh, there's another one right there, isn't there? Right? 3 right there. 3 right there. So we only care about 0 through there. So basically there's going to be 1s and 0s except for in those things. And yeah, okay, it doesn't mean overflow. Do y'all remember what it means? What does X mean? All right, looks like I ran out of time, so I'm going to tell you the answer in the chat. And hopefully it's going to be a visual that you don't forget. So let's turn my camera on at the end here. So logic 1 means true or on. Logic 0 means off or false. But logic X means you don't care. Okay, so we'll see this occasionally during the semester. The reason why we do that is because it actually leads to a smaller circuit. If you don't care what the output is, that means less wires and less work for you to have to do. See right here, it says 3 is not used. So we don't care what 0 plus 3 is right there, because it should never really get to 3. And I'll just do one of these right here because we didn't do any of the other ones here. The output Y is to be 1 if and only if the two numbers do not differ by more than 1. Okay. 0 and 0, they don't differ by more than 1. They don't differ by more than 1. Oh, they differ by 2. All right, so that's how you get started on that one right there. All right, I'll stop right here. I will stop recording, see if I have any questions, and then I'll go start recording on my own for the rest of this as a second video.